Sorry for the delay. I'm Nick. So today, three of us will share this lecture. So I will have an outline. So I will first talk about the model-free reinforcement learning versus model-based reinforcement learning, and then the global models. Then now we'll cover local models and trust regions, and then Kishaloy will talk about like managing overfitting in model-based RL and the other applications of. I don't think this is a correct outline. It should be image-based reinforcement learning. So firstly, this is a structure. We have two broad category of reinforcement learning. One is a model-free, that's covered for the previous lectures, and the one is a model-based. And the last lecture, we're talking that given the model, we can do the planning and to find the best trajectory. And for this lecture, we'll talk about if we don't know the model, we need to learn it. But before that, let's take a look at the basic differences between these two classes of problems. So for model-free reinforcement learning, we do not care so much about the model itself. So we focus on trying to learn the policy. So here we denote as pi. That means given any state, we want to find an action. And for model-based RL, instead, we are more focused on learn the transition itself. In this case, if it's a probabilistic case, we denote as P. It's a deterministic case, we denote as F. And so normally it will be sometimes more complex because it captures the transition. So for model-free RL, the advantage is it's easier to implement and tune comparing to a model-based RL, and also it's more popular. And as for now, and it have been more extensively developed and tested. But the disadvantage is it's not very sample efficient because since we do not know the model itself. So what we can do is just try to sample from the policy and just to try those actions, try and error and collect feedback to infer the reward and everything. So we need a lot of samples to do this kind of inference. And in contrast, model-based RL need less samples. And it allows the agent to plan by thinking ahead. So instead of just try to interact with the environment and get the feedback, we normally, if we know the model, we can plan a trajectories and to minimize the cost. So AlphaZero would be a good example because for when the model is given, so we can do the planning and to get the best strategy. But the disadvantage is we have a very complex optimization method, and also in order to solve this very to approximate this complex model, we make more assumptions and approximations, and sometimes this approximation might not hold. Then we will have problem trying to learn the real environment. So yes, as we said before, today we assume we do not know the model, so we try to learn it. So how do we do that? So we start with the algorithm version 0.5. That means we firstly run some base policy. If you don't have any knowledge, it could be a random policy to just do sampling and then to collect a data set. So the state action pair and also the next state. So we clear all the observations. And then we try to learn the dynamics model to minimize distance. So this is like a classic supervised learning to try to minimize the cost function. And then we can have a dynamic model, then we can plan through this model to choose actions. So the similar planning techniques as covered by last lecture can be used. But for this version, we do have some problem because of the base policy. we only explore a certain part, a small part of the space. So if when we apply those actions, when we go to some area that it has not been modeled before, then if we plan our actions according to our dynamic model, it might not perform quite well because of the distribution difference between the mismatch of data set. So the version 1.0 will try to solve this vulnerable to drifting problem. So instead of just rely on the previous collector data set, we will try to execute these actions, but at the same time, we will add the resulting data back to the original data set. So it's similar to Dagger. So we try to make the data distribution to be aligned to the model itself, and but there also got some problems because normally we will execute the whole trajectories before we enhance the model itself. We maybe will go too far already. So in order to solve this problem, the version 1.5 is we still do the planning. We plan the whole trajectory, but instead of apply the whole sequence of actions, we just execute the first action. Then we will do the observation, and then we will append the data to the data set, and we will replan. So we replan the whole trajectory, but we again only execute maybe the first planned actions.
So here, we just mentioned Dagger. You guys all know, because we actually didn't cover it at all in this class. It was one of the precursor lectures that you guys had to cover on your own on imitation learning. Do you guys want to recap that? Are you all okay with that? All remember what it was representing? No opinions? That means all good or all bad?
So maybe you could try to summarize in one question.
Okay. Do you want to try to explain what Dagger is?
Yeah, so in Dagger, what happens is like first you collect the data, then you have some initial policy, you run that policy, you gather some new data, and then you append the data to your initial data set, and then like this step by step. That's what Dagger is basically.
And do we all understand why that process is important? So Nick just outlined why we do that, why we add the data. Pretend it's final exam, right? So who can give me a reason outside of our presenter? I don't think so. I think it has to do more with stability, but maybe Praveen, you want to say?
So if we learn a policy and it goes through a certain state transitions, but if we make few mistakes, then we might diverge a lot. And then for those, we don't have samples. So we have to collect samples for even those and then retrain the policy.
Okay, so it has to do with this problem of high variance, right? When you step off the policy and then you have, you end up, your agent ends up in part of the state space which has never had any data for. So you're trying to mitigate that by putting these trajectories inside of your data set and then accumulate it over time. So it's basically adding more data and then stabilizing the agent over the training iterations. That's how I understand it. So Kishaloy, do you want to say anything else? Or?
I think I did.
Okay. So we'll proceed from here. So so far we covered the version 0.5 to all the way to 1.5. So we do see the advantage of version 1.5 is we can do this kind of correction for every step. So to avoid the accumulation of errors, even the error is small, but if you accumulate, it might make make a very big deviation from the desired destination. But the disadvantage is it's more time-consuming and computational expensive because we need to do this kind of scheduling and the planning for every step, and the planning is not cheap, right? Last lecture we covered this algorithms is quite complex, so the next version will try to combine some of the advantage of the policy-based reinforcement learning, but at the same time we try to learn the model. So this is called version 2.0. So the first two steps is the same, but the third step, actually, instead of just trying to learn the model itself, we backpropagate the error through the model function all the way to the policy to try to optimize the policy at the same time. So the good thing is later we don't have to do the planning to generate the action sequence. We don't have to rely on the planning, and we can just sample from the policy, which will be much faster, especially when we try to run the algorithm on, it will be quite efficient. So this will be a diagram. So we backpropagate all the way to the policy itself, but there are some problems as well. One big concern is if we choose the deep learning to, like, neural networks to model the model, so the states can tend to be correlated. So it's very easy that we will face either exploding or vanishing gradient problem. Okay, so that's the 4 versions of the algorithms. So what kind of model can we use to represent this complex? Yes,
in the previous slide, the third step, does that we backpropagate the f through the policy? Does that mean it is represented by the same same model? Like we use the same model for the same network for the model and the policy.
That's yeah, that's a good question. I think it's like an implementation kind of a question. If for neural networks, I think so. Please correct me if I was wrong. Yeah, that's my guess. But actually, we do have like other options other than neural networks. For example, later we'll cover, maybe you can use like Gaussian process. Then it might be a different story.
Typo 80 plus 1.
80 plus 1.
80 is getting repeated.
Which step are you talking about?
The third step is equal to the first step.
Oh yeah, maybe, yeah.
So can you point with the cursor which one you think has
so
the
basically,
typo?
like, he's giving rise to the new step, and that should give rise to the new action. It should be 80 plus 1. Right? That's not.
Okay.
Yeah,
You mean in the gray box on the bottom? Yeah. Okay.
Yeah, I think all right. Okay, so any more questions? Okay, so there are a few commonly used options to represent the system dynamics, Gaussian process, neural networks, and some others. So for Gaussian process, so this looks very similar to version 2.0. So just specifically, we use a Gaussian process to represent the system dynamics. So the advantage is it's very data efficient compared to maybe neural networks, because I think it's like kind of parametric because it's a Gaussian process, but it's not great with non-smooth dynamics. So so you want to know more details, I provide a link here to understand a bit more of Gaussian processing machine learning. But I think the intuition is if we have some observations, and there are some unexplored areas as well. But if the unexplored area is closer to the observation, then we are more certain about our inference, our guess, because we can do some kind of like interpolation. If it's further away from the known observation, then we are less certain. So this kind of assumption make make an intuitive assumption that it's kind of smooth, so can do this kind of interpolation kind of thing. So it will not perform very good if the dynamics itself is not smooth. And also it's get to be quite slow when the data set is big. So in the contrary, for neural networks, so we use a Euclidean training loss to train the network itself. The input will be the state action pair, and the output is the observation. And so it's good it can model like more complex losses as well. So the advantage is it's very expressive, and it have the power to use a lot of data. But at the same time, it's not good when the data size is small, because it tend to be a data hungry model. It's quite complex. And for other options, we can have like Gaussian mixture model. Or if we have some domain-specific knowledge, then we can have domain-specific models. For example, if you have robots, we can have the joins and everything. If it's a game, we have all the rules of the game. Yeah. Okay, so that will be my part. So later now we'll talk about the local models. So any questions so far?
Okay, hi everyone. My name is Nan. I'm from the same office as Nick. Just now, Nick mentioned so he talked about the global models, and first is why we use model-based reinforcement learning. First is the sample efficiency. We don't have it's like the model-free reinforcement learning. You need a lot of samples. We just for the model-based RL, we just did a limited set of samples. It's more efficient, and also it's more transferable and can be generalized. If you learn a single policy, it can only be good for one task. But for a similar environment, if you learn the model-based, if you learn a model, the model can be applied to some other task as well. But the problem with the global models is first your transition function. Your transition function, it could be a very big neural network or Gaussian process, and so the planner can go to the place where the models think things are better than where they really are, because they are trying to optimize this function. And also generally, it's very hard to find a good model to converge globally for a particular task. So and sometimes the model itself could be too complex comparing with the policy. So you can have a simple policy, but you need a very complex model, and it's very hard to get this model. So that's why it's just quite intuitively you think you should learn the model locally instead of globally, so it can perform well. A simple model can perform well locally instead of you're trying to find a very complex global model and converge at every stage. So this is the function we are trying to minimize. We're trying to minimize the cost function, but this time our constraint is the f function we don't know. So we also need to try to learn the f function, and what we really care about this constraint optimization problem, we really care about is the derivatives of f function with respect to the states and action. So how do we find this this local model? How do we find these derivatives? We process this. We run this policy, and we gather some samples, some trajectories from running this policy, and we collect data points. We collect a set of the trajectories, and then we're trying to find the derivatives on this on the trajectories. Correct me if anywhere I goes wrong. I had a so this is the procedure. The procedure is we run the policy to collect some trajectories, we feed the linear dynamics, to those trajectories, and then we use it to improve our controller, which is our local policy. And we need to add a bit of the Gaussian noisy. Like the first time, we need to add a bit of Gaussian noisy as well, because otherwise, if this is deterministic, we couldn't find this linear relationship. So because we assume in a local, in a very narrow local region, is a linear relationship. So the derivatives is just the linear relationship. The AT and the BT becomes the derivatives. Because that's our assumption. In a very short, if your trajectory is close to the how to say that. So in a very short region, it's gonna be a linear relationship.
So are we all clear why we're adding a noise term, right? That there's a normal distribution being assumed here. You want to try to clarify?
So if it is a deterministic, so every state and the next state is deterministic, then you couldn't find the relationship between this. There's no linear relationship between your current state and next state. Noisy, then you understand how the next state will change with some Gaussian noise. You know how the next state will change if you are changing your current state. You add noisy because you want to find out this linear relationship between the current state and the next state. Is that clear, or do I?
If it's clear, can someone else paraphrase it?
Is there a better way to?
Yeah, so that's why I'm asking, because I'm not 100% sure myself. So I want to see whether any of you understood the lecture, because I guess you watched it as well. How to explain why you're using a normal distribution to add noise when you have observations that come from the system.
So if you imagine, yeah, this is from lecture. If you imagine it's a linear regression problem, if all your sample points, if it's deterministic, your current state and next state will be like a single point, then you couldn't do the linear regression. If you add a bit of noisy, the sample points are a bit spread out. You can find the linear regression between the two variables.
Everyone okay with that? You guys need more explanation?
I think you're like kind of okay. So the f function, right? It's actually creating your next state, right? So like
yes.
your f x t and ut gives you what is your x t plus 1.
Yes.
Right?
Yes.
So I guess like that's the model that you're learning, like your
yes.
the model. That's what you're learning.
Yeah.
So I guess like if you had a model and it only outputs like xt plus 1, and it will always output xt plus 1 if you give him like the same xt and ut, and that kind of makes all your like the condition be deterministic in a sense. And I guess like his point, like I guess the point of adding noise is to just give it noise, because you're trying to approximate a function, but your function approximator is always going to be giving you one output. But you kind of want that sort of stochastic solution, so you add some noise to it, so you get like you see more stuff. Yeah, that's my understanding.
Right, I guess because of the deterministic output, you would only get a single point, right? So you wouldn't have enough data to do any regression. So the idea is to add some noise so that you get slightly different output, and then you can discern the type of signal that you want to try to mirror. And because local function approximation is always approximated with linear transformation, then there's no problem trying to do a simple regression. So you get a piecewise linear version of the function.
Okay. Clear about the procedure. And so that's the general procedure, and it brings two problems. The first one is like a controller to execute, and the second problem is how to stay close to your old controller, because if you have this linear assumption is your controller is close to the old controller, then you have this kind of a linear relationship. If it's too far, this assumption may not hold true. So which controller to execute? Actually, the lecturer provided version 0.5 and version 1.0, but I just came all the way to the last one, and it's a controller you cannot do the deterministic. Just now we explained you cannot do this deterministic. You need to add a bit of the Gaussian noisy, and why we choose this Gaussian noisy to be the inverse of QUU is this QUU stands for the cost to go. So it's like a measuring the relationship between your action, whether your action matters a lot to the cost. So you can inject more noisy, the action means less, and you can inject less noisy when the action is very critical. So this is the steps we trying to fit the linear dynamics. So you basically just do a linear regression to fit the dynamics, and there's a better way is suggested is to use the global model as a prior. In this way, because you have more information from the global model, then your local model may perform fitting better. So this is the linear assumption only holds true if your new controller to the old controller. Otherwise, the error could be very large. That's kind of the intuition. So you couldn't let the old controller go, the new controller goes too away. You can have a very small range. That's why we need to use a tool called KL divergence to restrain that the new controller is close to the old controller. Then your linear assumption holds true. So this is the KL divergence is to trying to find this trust region. You have to make sure that the two trajectory distribution is close to each other, and then you just set up a epsilon, and it has to be smaller than epsilon. They have the mathematical derivations from the lecture. I couldn't do better than the lecturer, so I just take the result. This is the part of the end goal is we're trying to minimize the cost function while we have this restraint. The restraint is our trust region. And there's another mathematical tools to find to minimize the cost while make sure your restraint function is satisfied while minimize another cost. So because it's like you hold one is a constraint, the other one is objective. So you need a special mathematical tool to solve this kind of problem, which is called a dual gradient descent. It can help you to find optimize the solution while the constraint holds true. And they do some mathematical tricks and to fit in the LQR to solve this equation. That's also in the derivative part is in the slides in the lecture itself. Can't do better for the mathematical part. Let me just
clarify something. Like just go back a few slides before.
Yep.
For this. So one more before, sorry. Right. So here you're also kind of there's like a version like the one that's skipped, which is like a version 1 or something, right?
Yeah.
Or 0.5. So like you're also adding noise here to make it kind of explore more. Right? So like essentially there's two places that you're adding noise, is it? Because this is actually the policy kind of you're giving a state, you're kind of the probability of an action given a state, and you're putting some noise here, and then you're also putting some noise at a given a state and action. What's the next state?
So there's two places that you're kind of adding noise in. Am I right?
Yeah, I think it's. Let me check.
Because this is your transition.
Yeah, this is the transition function, and this is the controller, the policy.
Right.
Yeah.
So you're adding noise in two places.
Yes. I think this noise is for the purpose of finding the cost and action relation, and like how many noise you should put in based on the how does the action matters more or less. It's for different. I think it's for different purpose. I actually on the math part I have a question on the math part, because when they derive to all the way to the end, this is my question. I didn't figure out from the lecture or from the slides when they derive the mathematics over here. Yeah, just a question. I have no answer for this question. It's over here. So they split it out and they put the second term to the first place, and then they put this expectation as a conditional expectation times the XT's expectation, and because then the second part becomes the negative entropy. And then when they combine the two together, I think there's some missing term over here. Is it? No, it's but how come this these two parts cancels out? The expectation of XT and expectation of TUT. So I saw that.
Why do you think there's a missing term?
XTUT will be the denominator, and well, the expectation of XT will become the numerator. So, but somehow this term just gone.
Can you hear me? No. Okay.
Now the question is between line 2 and 3. What
Yes.
happens?
Yes.
Why are you able to replace the two expectations with the
I
law
can
to
they are muted.
Yeah.
Never mind.
This is the negative entropy term becomes the negative of the entropy of
that conditional probability, right?
yeah. But then why the expectation part is just gone?
It's like incorporated function. That's how you do.
Okay.
Sorry, can you speak
So
up?
maybe like the expectation is already incorporated into the H function because it already has the XT parameter. I'm not sure.
Okay.
Yeah, define H that way.
Yeah, it might be because like when they're doing like the expectation over the PXT, right? Like and so like you know the difference between the expectation of PXT and the expectation of PX, comma UT, right? It's actually like the probability. Like the bottom one, right? It's kind of like the top one is like you kind of marginalize out the UT, and I guess it accounts for that. Like on top, and then bottom you're just expanding it back out into like the terms.
Yeah. I have no idea about this part, but maybe it's part of the H function definition of the entropy. Yeah. Okay.
Anyone have any other input on that? Okay, I guess we'll have to move on.
Yeah.
Hi everyone. So my name is Kishaloy, and I'm going to talk about like advanced model-based reinforcement learning. So I had been preparing for this lecture for like past 7 days, and I'm quite I'm quite fascinated with the way like Sergey has organized this many complicated things into a coherent course. So please forgive me if I am not that consistent, but I will try to make some justice.
Kishaloy has also the distinction of meeting Sergey in person, right?
Yeah, so I was doing an internship at Google, and there was this conference called Baylearn, which was being held at Facebook headquarters, and Sergey Levine had come there, and he gave the keynote speech on meta learning. So that was a nice experience of meeting him. Thanks for giving it up. So we'll first talk about like how overfitting bothers in model-based reinforcement learning. What's the actual problem, and how can uncertainty like creep in these models, and how do we fix it? And also like we'll talk about some of the model-based RL with images, because if you remember, like there is a clear distinction between state and observation. Like when you do not know the entire thing about your universe, then it becomes observation, right? So we will use like partially observed Markov decision process for this. And we'll also talk about like how deep learning techniques such as embeddings or like autoencoders can be used to address this issue. And we'll also talk about some of the dynamic sever encoding that can be incorporated, like where you are aware of the end goal of your task. Right. So Sergey like starts his lecture like with this example. This is from a paper. So the point he tries to make is like, if you look at this, so in this graph you can see like the cumulative reward is on the y-axis, and the training time is, or the time steps is on the x-axis. So the point he tries to make is that after some 10 minutes of training, that model gains some decent amount of reward, which is around in the ballpark of 500. But like if you keep on training the model free version like for 10 days, after 10 days the like reward is much more. So he gives 2 example videos with this half cheetah thing. So on the left it shows that the model based thing keeps running at a decent speed, but this model free version after 10 days is like running at a much faster rate. So the point he was trying to make is like, in case of model-based reinforcement learning, you have like a lot of parameters to learn. So if you're overfitting too quickly during this period of time, then your performance will tank, and you will never be able to get back to the desired amount of reward that you get. So the point is to make sure like you are not letting overfitting happen during this initial phase of the training. So that's the point he made. Yeah. So this was just an animated slide, so it comes over here. So now let's come to the analysis, like why the performance gap is happening. So we'll talk about the learning version that Nick introduced in 1.5. So you can see like, again, here it's just the extended version of Dagger. So we have the initial data, and then we are collecting more data through this dynamics model. And here, what he's trying to say is like, so this is suppose a 1D trajectory, and you have this reward function along this y-axis. So now these dots are the observed points that you have in your data set. So you can see like this point was not observed. This happened just because of the model idiosyncrasy, or the model was not able to fit that particular point. So for the entire system, it's very tempting to go here. Like, although we are not even sure like whether this is a correct point or not, but from the model's point of view, the model will always like end up being there. And the actual variance is pretty small. Like if this is the ground truth, this hyperplane or simple 2D line over here, so the variance is quite small, but still you will have high rewards because some parts of the data sets were uncertain. So here he brings some examples. Let's skip this. So now, yeah, we come to this. It's continuation from that. Here he is trying to say what I could understand from this point is like if your probability distribution that your model is outputting, if it looks like a Gaussian process, then naturally what would happen is like the uncertainty would kind of be inversely proportional to the amount of mass that you have, like under this normal distribution or whatever distribution you have. As for example, here you do not have any points. So I mean, at the extreme ends of the spectrum, you will see like the uncertainty is lot much compared to where the main mass is situated across this entire distribution.
How do you read that graph? So it's a 1D controller, is that right?
Yes.
And you're either going to the left or the right of 0.
Yeah, so I think he was talking about moment matching here. So this is basically the output of your model, which is not strictly a Gaussian model. Then they're using some sort of a statistical method called moment matching. I think it like logs down to the 96 confidence interval, and then tries to define a Gaussian curve to approximate that distribution. So this is the uncertainty based on this distribution, not the Gaussian. And what I interpreted was like where you have less amount of mass in this distribution, you will see like a lot of uncertainty. Like where you have lot of observed points, the uncertainty will be on the lower side. Yeah, let me know if you have any other thing to add here, or if you have any question.
Wonder how attendant request to make it. Some of the attendant want to say something, so and turn on the volume.
Oh, sure.
I hear them.
Do you guys have any remarks remotely? Turn on the volume so we can hear you.
Does it work now?
Yeah,
Hello?
it's working. We can hear you.
Yeah, hi, we can hear you.
Well, it's not about this or the previous thing. I was trying to explain a thing about the entropy thing in the previous presentation. Not sure if I mean we've moved on to that one, so I don't know if we come back on this. I just write it in Slack. The
Okay,
question that the previous presentation
go back to that one.
the lecture 11 thing.
You want to go back to that for a second?
You can provide up the cursor. You can change here to 11 and shift enter.
Okay.
Shift enter and then open.
Remove dot.
We're talking about very much towards the end here, right?
Yeah, I think it's towards the end. I'm not actually looking at the slides, but I remember that the goal was to show that the under x of the expectation under u given x, right? This one, yeah, this one, right? Moving from the expectation under x of the expectation algorithm is equal to just the entropy of u given x, right? So I think the trick that to notice is that there is a rule in probability that the expectation under x of the expectation under u given x is equal to just the expectation under x of something. So that the 2e, the two nested expectations will just become just one expectation under the right term. I think this is the thing that you are asking, right? Okay, I will write it.
Yeah, that's right. We were wondering how to step 2 to step 3, and how the two expectations collapse.
Right. I mean, I'm not sure. Maybe that maybe this is what was explained. I'm sure, but I just wanted to. Was this the confusion? How the two expectations collapse into just the entropy without any outer expectation? Is it what?
The question was how it expands back out into the probability xt and ut.
It's a kind of the probability of ut given xt.
Can you say it again?
The question is actually from the second last line to the last line, like how it expands back out from probability of xt only to probability the expectation with respect to the probability of xt and ut.
I mean, the thing is that the log of p of u given x, and the expectation of the logarithm of a probability is the definition of the entropy. It's just that the trick is about the collapsing of the two expectations. This is a rule of probability. I can find it somewhere on Wikipedia if you want, but the log of the probability of the conditional, this is going to be of the conditional, and that's the definition of that's part of the definition of the expectation. It's just that the two expectations will collapse into one because that's how expectations work. And that when you have the conditional inside, and then the the condition, the one outside, then it will collapse into one.
Yeah, we know the collapse, but it's more on the expansion from the expectation of pxt to the expectation over pxt and ut at from the second last step to the last step, the expansion out. We get a negative entropy collapse, but it's just the expansion out from the second last step to the last step.
Yeah, maybe we're talking about the different thing. I'm not too sure where I see the expansion. It just becomes the entropy, right?
Well, I think like main question
expectation term
from this from this term.
It's like an F2 button, so I can
the second line to the thing.
So isn't there like a spotlight thing?
And let me turn it on. Sorry.
Yeah. So from this like expectation over just this probability, how does it expand out to the expectation over this probability?
That part was already there. It's all inside the expectation of.
Sorry, this one.
Yeah, that's already there.
Yeah. So I think it's just a marginal. Is it correct? That was the question, right?
Yeah. In the second term, we should have this.
This term?
Yeah. So
no, this is here. But I thought the question was from this to this. Yeah. Like how do you expand from
I think we can prove this from the base
rule.
rule.
I think you can probably prove this.
So if you take like base rule, it just
Can you
becomes
speak up?
Yeah, if you talk about base rule, like if probability of something and something is so if you look about like A given B, it's probability of A union intersection B divided by probability of B, right? So here, if you define in that times, probability of UT given XT would be probability of UT intersection XT divided by probability of XT.
Right? It's collapsed, but
it's just this. How did this guy, like, is it equivalent from like basically like if can I just kind of swap like this into this distribution?
Yeah, so
like,
this
get, like,
this too is probably getting collapsed to this because in this step EP was outside this box, so this one is not multiplied with this, right? But here both the terms are inside and it's getting multiplied by this. So
no, this whole thing collapsed to H. So you can use this and then you can't.
No, but here if you look at the expression, like here the whole thing is getting multiplied by expectation of this.
Yeah.
Which was not happening here.
Yeah.
Here it's only getting multiplied by this.
Yeah.
So what I'm saying is like if you take these two together, you get something like this, and the whole expression comes inside the.
But you can't take those two together because this and this forms H. Right? Or well, maybe you can because he obviously did.
Yeah.
Okay, so maybe we can, in the discussion or the scribe notes, we can try to spend a little bit of time trying to deconstruct what's happening here. We want to do that so that we can be more clear about the map. Other comments from remote? Or does this clear it up or make it more confusing yet? Okay, so let's go back to Kishaloy's presentation on week 12. Yeah, it's already there. So we can turn on the purple F1. Function F1, yeah. To turn on and off. It's a toggle.
Cool. So let me resume.
So we were talking about this diagram in the lower right. So any more questions about that one? Oh, okay. Let's go ahead.
Yeah, so here he talks about like why Gaussian processes are so popular for model-based RL. He takes an example of a cliff. Like suppose we want to get a better picture of the entire ocean, then we need to find a place where you can see the maximum amount of sea. So there is also a possibility that you might fall off the cliff if you are like too enthusiastic. So when the model tries to explore, you need to be aware like how much uncertain your model is. If your bound is like too much optimistic, then there is a chance that you might end up being on the cliff and never get back up. But if you are sure that your area of exploration is much smaller, in that case you are bound to find a good solution. So yeah, so in that case what he's basically trying to say is like if you penalize like the exploration part on the basis of how much uncertainty is there, in that case if you penalize too much, then there would be like a lot less of exploration and you might get stuck on the same set of states over and over again. So there are a few caveats against this section width. The thing is like if you want very pessimistic value, then probably you can take the bottom 10% of what your model thinks of the correct estimates. If you want to be very much optimistic about all the possible rewards, then you take the like top 10% or something. So he also mentioned some papers that do this kind of tricks, but expected value in general is often a good start. That was his point. Nice. So next question is then how can we have models which are inherently uncertainty aware? Like, is there any way to model this? So first, he goes through some ideas. So first example is like, suppose this is the neural network model that you have developed for your, the second box in your RL loop. So the input is like the current state and the action, and the output is like what is the probability of the next step. That's what your neural network is trying to predict, right? So what he's saying, like if you have like categorical states, then you would have one probability distribution over all this. Then the entropy is very easy to define. And even if you're not having like categorical distribution, if it's a probability distribution like a Gaussian, then also you can come up with some sort of entropy. And you can always say like, okay, I will define like my model's uncertainty with this entropy. Like if my entropy is too much, then probably there is a lot of uncertainty in the model, and the other way around. But the question he asks is like, why is this not enough? Like you can always look at the model's prediction confidence and say like whether this there was certainty in this prediction or not. But his question was like, why is this not enough? Why do you like need to dig deeper? Is there any thing that you can think of?
Well, there's some reasons.
The notes are already there on the slide, but if you can still sum it up and.
So if you read the slide, can you answer the question that Kishaloy and Sergey posed? So why isn't it sufficient?
I think like the answer to that was that the entropy of that of doing or rather doing that will try to find fit to the noise in the data generation process. So it's basically the noise in the data generation itself. Like, but you're not like there's still uncertainty with regards to whether your model is correct to start off with. Those are the uncertainty that's not taken into account using these two methods. Not sure.
Thanks. Yeah, so I think you're right. So what he was trying to say is the model is trying to model only the data. So if you look here, okay, so for this portion, the data point was never observed, right? So he gives an example. Suppose we just want to model a normal car, and we have observed some values from the real world, which inherently is noisy. So in that case, the supervised neural network, what it will try to do is it will try to come up with a model which like minimizes the overall error, right? So that is like trying to model the noise that's present in the data, right? But the point is like we are not even sure like whether that presentation is a correct one. In other words, he draws an example on the whiteboard. Suppose there are some points on the 2D plane for classification, and you can define a straight line in 10 different ways. Like all of them will do correct classification, but you are not sure like which model to use, right? Yeah, so he comes to the conclusion that the model is certain about the data, but we are not certain about the model, like whether this is the correct model for all possible data or not. Cool. So here what he's saying is like we have this parameter space theta for this neural network, right? And usually what we try to estimate is the value of theta for which the probability of theta given this data would be maximum. And these two terms are equivalent because the Bayes rule, because probability of A given B is proportional to probability of B given A. So based on that, this model holds true. But he's saying that choosing that optimal theta won't be correct. What is the exact value of this entire distribution, probably of theta given data, like how certain we are about the parameters that we are learning, right? And that can be done through this integrational equation. So you can see like we have added one more parameter theta, and we are varying that theta parameter by adding this delta 3 and taking the integration over all possible values of theta. So this, if we can come up with this will tell us like how much uncertainty is there in the model, right? Fair enough. So in this respect, he talks about Bayesian neural networks. So the only difference with the normal neural networks is you have scalar weights for all these connections in case of a normal neural network. In case of Bayesian neural networks, you have like a lot of Gaussian distribution to approximate these weights. And the assumption is like these Gaussian distributions are like independent with each other. That's why you can take a product of all this, because you are assuming that there is no correlation. So he says that there are like a lot of parameters, and if you are going to tackle the covariances among them, suppose there are 1 million parameters, then the covariances parameter space would be like 1 million into 1 million, which is like untractable. So intractable, right? Okay, so right, so all these individual distributions would be basically giving you a normal distribution with certain mean and some sort of uncertainty about that particular weight. Right. So this first solution he proposes is kind of a bootstrap ensemble method to overcome this kind of uncertainty problem, which basically boils down to like you train a lot of different independent neural networks, and then you somehow combine all of their predictions, right? He didn't show an example, but I can tell you like what can happen in that case is like suppose one model predicts, one model fits the data like this, another model probably would fit the data like this. So if you can, combine everything together, probably the uncertainty would be removed. So that's the hope here. and it's basically a simple averaging. You can see like you train all of these networks and then you take the average of all these predictions. So that's how we can remove the uncertainty. And he talks about one algorithm which is based on like sampling with replacement. So basically one question crops up, which is like you have only one data set, then how can you train like 10 different or 100 different neural networks, right? So the trick he mentioned is like sampling with replacement, where like you have all the data samples. Then to make like several other splits, what you would do is like with some probability, you will pick one sample from the data set and you will choose the next sample, assuming that you had replaced in the first first pass. So if you do this enough time, you would have like n number of data sets to train your neural networks from.
That's just the general bootstrap principle, right?
Exactly.
Is it any different from that?
I don't think so. It's the normal sampling.
Okay. But I'm interested to know a little bit more about why this is so important, because when we train neural networks, we usually use dropout to do some form of model averaging, anyways, right? We're trying to smooth and make sure the neural net doesn't overfit by using dropout on features or nodes. So how does dropout differ from this technique? Anyone know or care to elaborate? He does mention something called concrete dropout. Did anyone look at that paper? No? Any thoughts on that?
So in this case, with the same small amount of data we're trying to get, we use it for different models, and based on its initialization, they have different things. And when the output is very different from each other, then we are uncertain about whether it has learned something or not. And then as we get more data, so maybe it can happen that these converts to because they're trying to fit the same thing, they converge to the same thing, and then the output same, so that we know that certain means it has learned the same things. So then our certainty increases that the model has learned something.
So when the variance from the different models is very low, then we're pretty certain that it's the overall ensemble has learned something. But when the variance is high, you don't trust any of the models in particular.
Are you saying that's the point of this, whereas we ask about dropout? Yes, dropout would be one.
There's a part of this. So I don't know how dropout would.
Dropout only give you one.
Yeah, dropout
give you only a single network.
Yeah. Yeah, that's true. So you wouldn't be able to look at the variance over several predictions, right? Because you only have one network.
You only have one. Unless you try to do fancy things.
So this is just a standard machine learning idea, ensembling using bootstrap samples, right? Am I right to say that? Is there anything more from there?
Yeah, there is more, but like that's in the next slide.
Okay.
Yes.
And I think it's not dropout, but in the lecture he mentioned, for example, LSTM, it's like a trick to modify the network itself to make it more like learnable. But he mentioned that the dynamics, the real-world dynamics, has some kind of like characteristics which are not just somehow randomly or creatively change the network structure itself. Probably be some reason we cannot just randomly drop out some of the connection because the network itself might not be so feasible or flexible if we want to model the real world.
Okay. Yeah, the RNN and the LSTM is good for getting some type of, not Markovian, but some temporal dependency from previous time steps. As you mentioned, I think is a bit of a hack, because you're just using existing architectures to try to get some type of desired characteristic.
Shall we continue?
Yeah.
Cool. So first he talks about this slide, then they conclude that this is a good theoretical framework of learning bootstrap based ensemble methods, but in practice, what works is like you start 10 different networks with the same set of data, but with different initializations of your internal parameters. Then the HTD and basically the random initialization will take care like that all the models are independent to each other. And he mentioned that there is no theoretical proof, but it always works good in practice. And they just laughed.
So this is just taking advantage of the fact that initialization is very important in deep neural networks, right? And so you get very different output with different initializations. So you're capitalizing it on rather than calling it a weakness, right?
Yeah.
So the bug becomes a feature. Is that right?
Yeah.
So is the recommendation just to do that, just to start with random seeds rather than try to bootstrap samples and then use the same random seed or anything like that?
He said like if you like end up doing that kind of random replacement based sampling, then probably it will take more time to generate the data rather than just initialize 10 different networks. So from an implementation point of view, this makes more sense.
Right. You don't have to load so much data. You only have one set of data, but
Exactly.
you start with different initialization parameters. It's eminently more parallelizable that way too. Okay.
Cool. So here, what he's saying is like we have all this sequence of actions. So we have like A1 to AH, and you would normally take the summation of all these time steps, right, for the reward function, where st plus 1 is basically coming from that particular model. And now you have like n number of networks outputting n different things. So basically you need to sum them up and take the average of, for the probability distribution across all these actions. Yeah, and then the algorithm becomes quite simple. So basically, you will sample one particular neural network to, get the observation. Then you calculate the reward, and then you again go back to step one, sample another neural network, compute the reward. So you keep doing this, and finally you accumulate the average reward for a particular action. Okay, moving ahead. So I think we have already talked about this. So because you're making the prediction via a neural model, the distribution may not always be a Gaussian, which is required to make it like differentiate later on. So what you can do is like you can use some tricks like moment patching, where you take one particular distribution, and I think you take this 95% confidence interval, and then you lock these 2 points and try to define a Gaussian between these 2 points, and now that's how we move forward. Cool. So here he goes back to the initial paper that we had shown earlier to talk about the effect of overfitting in this learning process, and it sees that as you have seen earlier, like with 10 minutes of training, the model was achieving somewhere around 500 of reward. Like if you do this kind of ensemble-based training, then you get reward of what's in the ballpark of 6,000 to 7,000 within reasonable amount of time. Yeah, so about 10 minutes of real time. That's what he mentions.
So one graph says cheetah, the other one says half cheetah. Is it the same?
I think so.
Okay.
So it has like 2 legs and half of a mouth. So
I see. It's a 2-leg cheetah, so it's symmetrically cut.
cool. So here he mentioned some papers. which might be interesting to look at.
So
Yeah.
how would we go on about this? So when our models are uncertain about predicting, so then we don't plan and then we explore, and when they get certain, then we plan more. Is it?
I think it's the opposite, right? He's worried about the case where you get a reward estimate that's really high, but is quite uncertain, right? Not locally close to your current policy. So you see something off in the distance that looks really good, but if you go there, it's like a mirage. You'll fall off the cliff, right? So the idea is again, don't put a lot of emphasis on high variance rewards that you might find from a single prediction, right? If you ensembled it and you see high variance, then you're just saying, well, it's probably a mirage. I don't want to trust it too much and go in that direction. Rather, I want to go someplace locally good, right, and move in that direction. That's what I understood.
So the algorithm just takes, show the algorithm.
Oh, sure.
Takes the average. Just takes the action. It looks at all possible actions and then it says pick the one that has the best average. Is that something like that?
The step 3 says calculate the reward as the reward over the trajectory, right? And then take the average reward, right?
Candidate action sequence. Sample.
So can you guys identify where the uncertainty is in the algorithm?
I think it's just averaging the what over the models, the different models, so that you don't pick a model that's over optimistic. Looks like it's averaging it. Sample the step 1 is going to do that k times, and just going to average it over the k times.
Okay, so can I repeat or paraphrase? So in step 1, you sample several neural networks.
Single neural.
Yeah, actually, like you have n number of neural networks, then you sample just one.
Okay.
Then you run that, and then you see. Yeah, you're gonna step 4 says do it again.
Yeah, I think the idea is like take the reward at each time step from different networks. That's what it boils down to, right? Because it's going from 1 to h. And then like
no, so it's a candidate action sequence. That's the whole sequence. And so it's asking how good is this plan? I guess an action sequence of plan.
Mhm.
How good is this plan?
Yeah.
Let me evaluate instead of
I see,
picking
yeah.
a single data to evaluate this plan. Let me average out the quality of the plan over whatever.
Right, yeah.
So can I say steps 1 through 3 is run on one neural network,
So,
and you do this k times in parallel?
So you get k neural networks.
So you run steps 1 through 3 on k neural networks in parallel.
Yeah.
You aggregate all of the performance in step 4.
And that
And
tells
then
you how good the plan is.
Okay.
So you don't depend on a single overfitted neural network.
So the complexity is something like number of networks into number of steps, so H cross N.
Right. Yeah. I guess I misread step 4 as being serial. So after you do step 3, then you go back to step 1 and do it again. But what you're saying is this is a parallelizable process, right? Steps 1, 2, 3 constitutes a single process for one neural network approximator, right? And you're just saying do it many times, so that you get some more reliable estimate of how good the plan is, rather than looking at one data point.
Single possibly.
Right. So then here, there's no guarantee that you need to stick close to the current plan. It's just to say
just averaging
average to avoid
to avoid
overfit.
a single
Okay.
network.
So yeah, so after the break, like he talks about some of the pragmatic examples. He shows some videos. So here is an example for model-free RL with images, and it does pretty well. So his question is like, can you use model-based methods with images? So here is the thing, like in case of model-based RL, the only observation we have is like some sort of image that is captured by a camera, right? So the POMDB like kicks back here. So he switches back from the S and A notation to X and U. So those are the same thing. So you can see like if you are in a particular state X1 and then you observe something O1, then you come up with some action which is U1 and you go to step X2, right? And the Markov independence property means that to talk about X3, you only need to see like what happened at X2. You do not need to go back to X1. That was the Markov property. But he also mentions that that doesn't hold true for the observations. The observations might be linked to what happened in the far past. Right. So here, like learning in latent space can help us. So the idea is to learn an embedding, which is the function g of the observation, and that entirely is learned in the latent space. That can happen like both in the model-based and model-free form. So here, what happens is like given this observation, the neural network will give you back some sort of embedding, which you would use to use in conjunction with your policy to come up with the action. Now the question is like, how do we define this embedding? It can be like it can be defined in an automated manner like autoencoders, and it can also be defined in a way where the network is aware of the end task that it is performing. Right. So this is a model-free way that he mentioned. I didn't quite get like what exactly this paper was doing, but he said like this was an old paper who were trying to like come up with this G function. Then they were using this G to influence the policy directly because that's a model free. We don't have a model, right? Yeah. So the idea is something like this. You have the image, then you have this autoencoder decoder model. So I think you all know what happens in autoencoder decoder. So basically we have a network where the network tries to replicate the input in the output, right? And then there is a bottleneck layer which has like lesser dimensionality compared to the output layers. And the idea is the network tries to compress whatever it sees so that it can recover the entire sequence in the output. So they take the output of this bottleneck layer, assuming like this is kind of a compressed representation of the input, and they use that to improve the policy. So that's how that paper like uses this embedding space, and it's low dimensional because obviously it's coming from a bottleneck layer where dimension is much smaller compared to the actual number of pixels. Right. So here there are some advantages, like you can learn the visual skills very efficiently because you are essentially compressing the whole thing, so you do not need that many parameters to learn. And the thing is, the cons are like it might not recover the right representation. I think this is a generic disadvantage of any autoencoder decoder, and also it may not be suitable for model-based methods because you are not really trying to predict the action of the state, right? You're just trying to improve your policy based on whatever embedding you're seeing. So now he talks about how to use these embeddings in a model-based manner, right? And the idea is quite similar. So I think they talk about a particular paper where they take like 3 channels, like red, blue, and green. 3 channels are there, and they learn a different feature for each of these 3 channels, and then they look at this difference between the target and the source image using like features from all these 3 channels, and they learn the embedding in that manner. So you have the idea of like what's going on in task.
Sorry, can I ask?
Yeah.
Does anyone know what is spatial softmax? Like the last layer before the feature point.
Okay, this one.
Because you were saying that he softmaxed it, but I'm not sure like whether it's like basically.
I think across, because he gave an example on the whiteboard, like you have one set of features from the red channel, one set of features from the blue channel, and then you take softmax like across all these channels to match the.
Not softmax, like one channel that you get, like you softmax it, but across it.
Yeah.
Okay.
So that was like drawn on the whiteboard. I'm not too sure about that.
I'm looking at the definition based in TensorFlow, and it says that it computes the expected position, 2D position of the points of maximum activation for each channel. So you will get an X and a Y for each of the M channels.
Maximum activation.
Yes. So it's like your softmax, but you apply it to each channel. Seems to be the case across the space.
Okay, so I think that explanation is not congruent with his explanation.
Yeah.
So I think it's got to be one of them. My understanding is something like the spatial softmax would be more like your second explanation, which is saying, you know, I have a 2D spatial grid, right? And I'm doing softmax in that region, right? So it's sort of like a pooling operator, right? Where you're saying I have a field of view, maybe a filter of 3 by 3 or something, and I'm pulling out something as a maximum value.
So the probability of one is spread across like the whole channel.
Yeah, that's what I'm guessing.
So if you are doing like black and white, then your softmax, and if there's only one channel, then your spatial softmax is just the softmax. But if you are RGB, then it will look at the softmax for the red channel, and it will give you the softmax for the green channel. So you get three pairs of XY.
3 pairs of XY. Oh, so the XY is actually the maximum activation.
Yeah, because you want the position. So it's like it's a 2D. It's
Yeah.
the XY coordinate
Yeah.
for one. Then each of the channel you have pairs.
Yeah. So you actually say that like the picture over there is it's like I think the dots visualization of 2 features point, but I see a lot of dots, so I'm not quite sure like what does the image actually means, like if everyone has any idea.
So you mean the picture on the bottom?
The bottom, yeah, the one with like all the green
all the
and
red and
dots.
green and
It says that it's over visualization of 2 features point, but I'm not quite sure whether he meant like visualization over 2 features axis or point. Like, because there's a lot of points there, it's definitely not. I mean, or it might have been like features point over time. I'm not quite sure.
it looks like a trajectory to me. I don't know, because at least the right one, there's just lines or something, or some artifacts connecting the dots, right? The red dots. Yeah. So I would guess that looks like a trajectory over time, and then the colors are trying to tell you where's the start and the end point. But I could be wrong.
Yeah, so I think here the goal is to place that white thingy inside the hole.
They use the spatula as the robotic arm, right, to
Yeah.
move the white packet of whatever it is, a bag of rice, it says up there, right, and then put it into a bowl. Okay.
Cool. So I think this he was using animation, and he was saying like we are not using states here. So because this is a model-based RL, right? So for each of the action, we would need a reward function in this case. And I think he was talking about some heuristics, like how they calculate the reward. Like there are some target points in the end task they want to achieve, and there are some initial points where the object is currently placed. Based on these distances, they were trying to come up with some heuristic-based reward function. Yeah. This is example from another paper which talks about I think joint modeling, where they were trying to learn this G and this distribution together, like not learn this separately through an autoencoder or something like that. They're trying to learn these two things together. So that was another example. Yeah, here he shows some videos about inverted pendulums and all those things. This is another example which like works with the local models that we just saw in the last presentation. So the idea is here you would add some sort of linear dynamics to your embedding model, which is kind of consistent with the control planning that you are doing. I'm not too sure about it. Maybe you can correct if you have any. In the last presentation, we saw about the linear dynamics, right? So here in this model, like to come up with the next state, they're like adding some linear dynamics to this embedding space.
What do we mean by that? How does it get added? So, for example, it looks like there's a new a variable here, right? The f and the covariance, or whatever that is.
Mm-hmm.
So, what do those stand for?
Yeah, so he just mentioned that we would use the linear dynamics from the local models. So what I'm assuming is this is like an RNN, and when you are coming to the next state, apart from the previous state's output, you are also like adding some linear component to it. I was not too sure as this was a separate thing.
Anyone have any intuition on why you would do that? So is it the same reasoning as we saw in the earlier part of the lecture, where we need to add some terms to get a more accurate local representation?
Well, I think he said like you're adding the linear model because like if your planning is if the way you're planning it, the way you're learning your model uses some sort of, rather the way you're planning it is doing the linear approximation, the regression. So then maybe you like when you're learning the embedding itself, you want to have the embedding that kind of really have a prior of linear dynamics. So then it's easier for you to just it's easier for your regression. I mean that's something that he said, but I'm not sure.
So then it's some type of way of constraining the embedding.
Yeah.
So it doesn't have, maybe exponential values or things like that.
Yeah, he wants. Yeah, you want. He said like maybe you want the embedding to kind of have the linear dynamics embedded. But that's all prior knowledge, so that's why the prior.
Okay.
Yeah, so this is an interesting portion of this presentation. Here he mentions like we are always trying to come up with the next state, but what if we try to like use the neural network to predict the next observation itself and use that to govern this learning policy? So what he's trying to say is like in both these arrays, the starting image is the same, and they train the neural network in such a fashion that it can predict the next frame of the video. So what if it, the system can use this prediction, like what if the arm moves over there, how would the resultant picture would look like, to predict the movements, and that's how it plans like what the trajectory should be to make the source image to become more like the target image. So that's how this paper like uses directly learning the next observation given this current observation, not really the states or the other components. And I think they mentioned they trained this on like generic videos first, like where it's easier to predict what would happen in the next frame, and then they used some weights from that particular model, to use in this kind of experimental setup as well. And in the actual presentation, there are a lot of GIF images that shows the movements of the robotic arms and how it interacts with the world.
But can you hold that assumption that the observation depends only on the mass?
So if you're defining the network in such a manner, you don't need to assume that, right? It's a completely free RNN. Like it's going through each of the frames and trying to predict like what the next one would look like.
So we use RNN when we have representation of all the.
Yes, theoretically, yes. You have the memory in the cell itself, which keeps the important parts from the past.
So here, the neural network is explicitly breaking the Markovian assumption by using the RNN, right? An LSTM or any other form of RNN.
Yeah, so then, as I said, like they use some heuristics based on like some designated pixels around the mean of the subject, and they try to predict like, okay, if I basically need to move this point from here to here, then what are the possible frames like? And then select the actions on the basis of that, because you can see the whole, what the next observation is going to look like if I take this action.
It's like visualize your actions with the goal in mind. Can I say that? So I imagine what it looks like to get to the goal and see where I'm going. And then with that in mind, locally I plan to try to match what I want to see in the output.
Yeah, so here they perform the experiment. Basically, you need to start from here and push the stapler to this particular position. And they will show a video like where the arm is like trying to populate all possible next frames and thus trying to capture like what the sequence of action should be. And here he talks about like a lot of domain-specific heuristics that you can take. Like suppose if you're playing a game, like what directions can I go? Like if I go to this particular direction, how much health score would I lose, how much, you know, armor would I get and stuff like that. But he said like these are always not scalable because the heuristics are totally like domain dependent, so it might not work for generic RL problems.
So how is this different from predicting reward? It's just a surrogate reward. Could I say that? It's not task success, but some other reward function, right?
I think here you can use some like kind of bootstrap knowledge, because you can pretend all these image-based models, right? What the next frames can be. It doesn't need to be trained on that particular environment.
Okay.
Yeah. So here,
That was the last
yeah,
slide,
that was
right?
the last slide.
So a question about this latent space. Am I going back to the slide?
Can you speak up a little bit?
Oh, sorry.
Sorry.
Will it be alright if go ahead? Yeah, okay, that's a good one. I'm not sure I understand where the partial observability comes in. Because from what I understand, you get the image and then which is your observation. You extract some information from it, some features,
Right.
to the autoencoder, and then that means that the features you get is some sort of subset of what you already observed. Isn't that less information than because in this Markov assumption, you call something a state when it's fully observed, and tells you complete information about where you're at.
Right.
And treating as taking some incomplete observation and making it complete. But I don't know. It seemed to me that using the autoencoder is going the other way. You're making something more condensed rather than augmenting what you missed out originally.
Yeah, so definitely the autoencoder is compressing, right? It's compressing and hopefully getting rid of a lot of noisy input values, right? So you have a more dense representation of the input. But I didn't quite catch what you meant about augmenting and about the Markovian assumption.
I think his question is like, in this case, the observation is basically have equivalent of having less information than the state, right? And we are using an autoencoder to even compress that observation. So how is it like adding more information to make the decision? I think this was your question.
I don't think it's adding more information, but it's distilling information, right? So sometimes, you know, in the visual space, you have a lot of information that's not really useful to the task. So I think the idea is if you do an embedding or some type of autoencoding, right? You're trying to get rid of that spurious information that could, you know, if you model it, you'd get noise, right? And it may cause adverse problems, right? So yeah, I don't think it's trying to increase the amount of data, right? It's rather trying to improve the signal to noise quality in the input. Yeah. But in the at least the naive version, it's completely independent of the entire pipeline, right? So the idea is you just have an image and you just compress it down by doing embedding.
Right. That's what I understood. Yeah, I understood the same thing. I was just trying to link it with the initial argument about situations where partially observable, you mentioned partially observable part of the decision process.
Yeah.
Or turning the latent space was better.
I think the main difference is the POMDP came here into picture because we are talking about images. Like suppose in other sorts of robots, you only have suppose limited sensors, and that can vary, only between few values. But if you have images, then the curse of dimensionality hits you, right? You have one image which is like 2 megapixels, so you have around 2 million values to consider at each time point. So how do you use that kind of information effectively in this framework, right? So it's kind of using the power of that image processing and in somewhat meaningful manner. In other case, you would have probably a vector of 5 values. That's fine. That's probably manageable, and you can still run all the transition operators and stuff like that. But if you have this much, you can't.
So the understanding that you have is that doing the embedding is sort of a dimensionality reduction operation, right? So that you can get a lower dimensional space for the representation of the observation.
Yeah, so my understanding is somewhat similar. So if you're trying to play chess or AlphaGo, like you have the information about the entire universe, right? And here they are talking about using some sort of camera that's embedded onto a robot and whatever that camera can see. So the space is somewhat different. At one case you are observing everything, and the other case you are not observing everything, but you have some rich, immaterial information available, which makes more sense, I guess, in a real world scenario as well.
So here the autoencoder would try to regenerate the same image because we're trying to factor out what's important from the image. Then the small, the dense representation of it should regenerate the image.
Yep. So there was one question in the lecture, like, then why are we even training what are we doing with the output layers of that autoencoder architecture? And the answer he gave was like, to show you these videos. So basically, you can always visualize like what was going wrong in this training process. Like if you see like, okay, the next prediction itself was wrong of the next frame, then you can be very certain that, okay, there is something wrong with my, the neural network that I have trained. That's why this is going haywire.
Do we need to spend a little bit of time discussing autoencoders? Everyone understand and the purpose of an autoencoder and what it's doing? How does it make a sparse representation? A dense representation from a sparse voluminous input?
I had the idea that if an input is sparse, then we can have a dense representation by one layer of the network, and this representation can be used in an end-to-end task to learn this representation. But in autoencoder, we're trying to regenerate the input, so it does not have the information about the task we're trying to. Just trying to somehow compress it so that we can regenerate the image, but then we don't know about the task, so we don't know what is important. Means if like in a game, the only thing important is my position of this thing or position where I'm at and something. But autoencoder will try to regenerate the image, whereas if it's an end-to-end task, we know what part of it is important. So the end-to-end can give us a denser representation.
So I think the autoencoder doesn't have, like you said, it doesn't have any notion of the task, right? It just says, can I regenerate the original, but using a bottleneck layer so that I'm forced to make a trade-off and summarize things rather than pass everything through, right? So one way to think about it is, let's say you're playing a game of chess, but instead of given the digital board position, you're given a camera to look at the chessboard, right? So what you would want to recover in the bottleneck layer is actually that digital representation, you know, pawn on whatever square, knight on whatever square. That's a very, very compact representation compared to the very large raster image that you would capture through a camera, right? So imagine if you had the bottleneck layer, like say this encoding of where all the pieces are, right? Then the top part of the network that's expanding from the bottleneck is just using that board position information to regenerate the picture, right? And the bottom part of the image, bottom part of the network is taking the image of the board and trying to say, okay, I recognize there's a pawn here, there's a queen on this square, and then generating that bottleneck layer, right? So it's some type of compressive, summarized version of that image, right? Yeah.
I think like I think that's a good explanation. So maybe it's a bit like saying that the autoencoder, you don't really care because it's basically kind of like how a grandmaster would look at the chess position, and the grandmaster doesn't represent everything together, but the grandmaster would say that he divides up the board into certain areas. Then he picks out what are the important features, and then he stores this as count representation. Then he can recreate the entire chess position from his mind. But what this also helps, and what might, I think, doesn't necessarily have to be with the task. So it's like this, you can say this autoencoder is kind of like the memory, but the task is actually you want to win. But it could be that you would get better ways to do the task on how to win by using this compact representation rather than by using the entire picture of the chessboard.
I think your example is closer to the one that is on the slide now, which is that you want the embedding that models and is somewhat sensitive to the task, right? If you think about an autoencoder for chess, a grandmaster's representation isn't actually trying to reproduce the original input. It is a representation that is catered to winning the game. Like you said, maybe the grandmaster doesn't care about pawns in certain positions because they're sort of like not very important, right? But if you're trying to recreate the original input, let's say of a board, then all of the pixels are equally important, right? So then you would need to try to get as close to the image of the chessboard as possible through your autoencoder. So
okay, maybe not a grandmaster. Maybe say a person who has played some chess, but it's not the grandmaster. So obviously his representations are maybe not as refined as a grandmaster, but because he knows the rules of chess, he can memorize the features in a more compact way than say someone who totally does not know what chess is.
Right, right. So it's a compressed representation. You could also think of it like if I have a raster image, but I could make it into a SVG, right? Some vector format. So vector formats are very semantically good because they can compress all of that information into a vector, right? So if you compare it that way, that makes also sense to me, right? So you're saying I have a letter A here, it's this size, this orientation. There's an arrow here of this size and this orientation. And then when I render that into an image, I have to take this symbolic representation and build a raster image out of it, right? But I think the key here is that the embedding, when it was originally discussed in the first part of this lecture, is task agnostic, right? You just have the input, which could be anything, but in the cases that Sergey showed would be a visual input, right? And then the autoencoder is exactly trying to reproduce the actual image that was input, right? Without any differences. So it has no idea about what's important. It's doing pixel by pixel loss or a suitable loss function to say that the original is this far from the regenerated image. right? But I think later they were saying, we want to embedding that's sort of like task oriented, right? That just catered to actually solving the task. And you see that a lot now in natural language processing. A lot of the word embedding models that are being created are task specific. Yeah, they have specific structure. Some of them are not task specific, but trained on multiple tasks, so multitask embeddings are also very useful. So for example, if you're learning to grasp, in a robotic arm, maybe having an embedding of that feature or that image would still help you with being able to move cups without spilling, right? Because they're somewhat correlated. If you can grasp well and you don't knock over glasses, probably you can also use that skill to move containers of liquid that are open topped, right? So that's been the case in NLP, that instead of training for a single task, you train for a whole bunch of tasks. You do the embedding that way, such that you get some joint rewards from that. So I imagine that would be helpful in robotics cases, because there's only one physical world, right? So everything has to still interact with those laws.
Yeah, and also if we look at the kind of task these papers do, we'll see that these are not as complicated as like solving a chessboard or AlphaGo. It's like more of what happens in a lab experiment kind of scenario, like some pieces of things are, piled up over one over the other, and you're just trying to do something with them. So I think depending on the problem, the solution also changes, right? So this is just one of them where you're trying to look at like imagery data and take the decisions, not the actual sensor results. Like the example Min gave, like for the chessboard, the chess master might be interested in figuring out where the exact things are, where the pawn is, where the king queens are, right? But suppose the task is like, okay, the chessboard is there, but I need to move one object from here to the other end. Then the embedding space need to learn, okay, this is just a solid object, and I need to either like avoid it or push it away or something like that. So in that case, like we can have like all the knowledge that we can gather from something like ImageNet, where it has all possible, pictures of cats and whatnot. And also if you have some task-specific data annotated, you can learn from that.
Okay, so I guess we've come to the end of today's lecture. Let's first thank all of our presenters. So if there are any comments from remote, we'd love to hear you. Otherwise, again, please be reminded that project titles and abstracts need to go up soon. I'm sorry, I've been a little bit behind, but I will try to get you all put into the STEP system. And I think next week we have week 8. Our week 8 presenters are here. I think Wei Xin is here. Anyone in week 8 helping out for week 8? Yeah, so please talk among yourselves and see whether we can get things started for week 8. Okay, thank you very much, and we'll see you next week.
It's gonna be presenting. So how do you